Okay, hello again, everyone. We're going to continue with our discussions of weak acids and bases and talk about an important application that describes the chemistry of these weak acids and bases, which are namely called titrations. You're familiar with these already from your high school course. You would have become more familiar with them in our lab before we had to make the lab virtual, but you'll get to do the calculations and so on anyway. So titrations, as you probably already know, essentially acid-base titrations, that is, consist of a neutralization reaction in which the acid component, the hydronium ion, and the base component, for example, hydroxide ion, neutralize each other to form water and leave behind a salt of some kind. So we're going to talk about various aspects of this for different kinds of acid-base titrations. And we're going to look at things like what's called the equivalence point, or otherwise known as the stoichiometric point, and the shapes of the pH curves that accompany these titrations. So the first of these that we'll discuss is the simple strong acid, strong base type of titration curve, which is shown on this example here in the lecture notes. This is a simple example that plots the pH as the progress of added sodium hydroxide amounts when we're titrating a strong acid, in this case 0.1 molar hydrochloric acid, 25 milliliters of it, and we're titrating it with 0.1 molar sodium hydroxide. Well, since those two concentrations are the same, we know that we'll have to add 25 milliliters of sodium hydroxide solution to exactly neutralize the 25 milliliters of hydrochloric acid solution. Well, if we look at the pH or measure the pH during the progress of the titration, we'll see the classical type of pH curve for a strong acid, strong base titration. The pH starts out at 1. 1 because we have a 0.1 molar solution of hydrochloric acid. So the hydronium ion concentration is 0.1, 10 to the minus 1, which means that pH is minus the log of that, which is plus 1. So the starting pH is 1. As we add sodium hydroxide solution, 5 milliliters, 10 milliliters, 15 milliliters, and so on, the pH will gradually increase, okay? But it doesn't increase all that much. In fact, in going from 0 added sodium hydroxide up to 20 milliliters, when we're 4/5 of the way toward neutralization, the pH is only increased by 1 unit, in fact. And at 12.5 milliliters, of course, it's referred to as the half neutralization point. For a strong acid, strong base titration, the half neutralization point has no particular significance other than that it's halfway there. As we'll see for a weak acid titration or a weak base titration, the half neutralization point is more significant than that. We'll get to that later. So with further increases of sodium hydroxide added, the pH will continue to go up gradually, but then as we get closer to the equivalence point, it starts to go up very sharply because the pH is a log function after all. And when exactly 25 milliliters have been added, we're at the equivalence point, or stoichiometric point as it's called. And so at that point, the pH, because this is a strong acid, strong base titration, the pH will be exactly 7, because what we've done is we've exactly neutralized all the hydronium ions of the hydrochloric acid with an equal number of hydroxide ions to form water. So what we have at this point is simply a solution of sodium chloride. Sodium came from the sodium hydroxide we added. Chloride came from the original hydrochloric acid. So we have a solution of sodium chloride, which of course are two what we refer to as neutral ions, the sodium ion and the chloride ion. So the pH is exactly that of pure water, or 7. Well, if we continue to add more sodium hydroxide beyond the equivalence point, of course, the pH will go up even further. And by the time we've added 40 milliliters, the pH turns out to be about 12, between 12 and 13. And it's due almost entirely at this point to the concentration of hydroxide ions in solution. So this is the classical curve for a strong acid, strong base titration. Now, another type, which we'll spend more time talking about, are strong acid titration with a weak base or a weak acid titration with a strong base. Now, as we'll see, there's a less sharp change in pH at the equivalence point, and the pH will be either less than 7 or larger than 7, depending on which way we're titrating, either this titration or this one. So looking at that, here's an example of a weak acid, strong base titration curve. In this case, instead of 0.1 molar hydrochloric acid, we're starting with 0.1 molar acetic acid, which is a weak acid, but we're still titrating it with 0.1 molar sodium hydroxide, same as before. So again, because the two concentrations are the same, we know that we'll have to add the same number of milliliters of sodium hydroxide solution, 25, as the volume of acetic acid we started with. But the pH behavior and chemical behavior is different than it was for a strong acid, strong base titration, as we'll now see. First of all, the starting pH is not 1 for 0.1 molar acetic acid. If you work out the equilibrium calculation for a 0.1 molar acetic acid with a Ka of 1.8 times 10 to the minus 5, you'll find that the pH is around 2.88, which is shown in this little table here, not 1. So as we begin to add sodium hydroxide solution, again, as before, the pH will start to increase, and it will increase until at the half neutralization point, which is 12.5 milliliters of added sodium hydroxide. At this point, what do we have? We essentially have a solution at this point that consists of the remaining acetic acid. Half the original acetic acid is still there, and we have the other half converted to acetate ion at this point. So what we have at the half neutralization point for a weak acid titration is a buffer. We have a 1-to-1 buffer of acetic acid and acetate. And for that reason, as we saw in the last lecture, the half neutralization point would correspond to a pH that's equal to the pKa for a 1-to-1 buffer solution, the Henderson-Hasselbalch equation we talked about last time. So with further increase of sodium hydroxide, and you can't see the red line because it's under this red bar here, with further increase in added amount of sodium hydroxide, the pH continues to gradually go up until we now approach the equivalence point, and as before, it goes up more sharply. And by the time we've added 25 milliliters, which will exactly neutralize 25 milliliters of the acetic acid, we've reached the equivalence point. But now, unlike the situation for a strong acid, strong base titration, where we essentially had pure water plus two ions, the sodium ion and the chloride ion, as we saw before, at this point, what do we have? We have a solution of sodium from the sodium hydroxide and acetate from the acetic acid. The proton from the acetic acid and the hydroxide from the added hydroxide, sodium hydroxide solution, have combined to form water. But what we have now is not a neutral pH solution. We have a solution of sodium acetate, and because acetate is the conjugate base of the weak acid, acetic acid, the solution at that point is weakly basic, not neutral. And so the pH turns at the equivalence point turns out to be 8.73, follow right about over here. And the reason for that is because this is a solution of sodium acetate. All the acetic acid has been neutralized to form an equal amount of acetate ions. And so as we saw a few classes ago, the pH at that point is determined by the Kb of acetic acid. And so, as it turns out, that pH corresponds to 8.73 because we have a solution now that is, there's a total volume of 50 milliliters, and so the solution is 0.05 molar in sodium acetate. Well, again, with further additions of sodium hydroxide beyond the equivalence point, the pH increases and eventually winds up at about between 12 and 13 as before. And the reason that the pH at this point is essentially the same as it was for the strong acid titration is because the pH at this point is determined almost entirely by the excess hydroxide ions. We've added 15 milliliters more of sodium hydroxide. And so if you calculate the pH of that equivalent solution, it's all due to the hydroxide ions. And so the pH is essentially what it would be for a sodium hydroxide solution with that volume and that concentration. So this is the difference between a weak acid titration and a strong acid titration, in both cases with a weak base. So what about looking at how this compares now to, lower this a bit so we can see the whole curve. What we saw, this little figure compares the behavior for the strong acid titration, which we just saw for hydrochloric acid and sodium hydroxide, and the weak acid titration, which is this, with acetic acid and sodium hydroxide. As we know, the equivalence point for the strong acid titration is at a pH of 7, which is right here. It's not marked on these curves, but it's right where the blue line and the red line intersect right here. And so the pH at that point is 7 because the solution is essentially sodium chloride. But for the titration of acetic acid, now the pH originally starts out higher than it did for hydrochloric acid because acetic acid is a weak acid, and the pH increases with the increasing amounts of sodium hydroxide. The half equivalence point is right here, at which point the pH is essentially the same as the pKa for acetic acid. And this whole region between about 1/10 neutralized and 90% equalized is called the buffering region, because in that region, what you have is a buffer of acetic acid and acetate ions that range from a ratio of 1 to 10 up to 10 to 1. And so the pH change here over this whole range is about 2 units, depending on the concentration of the acetic acid that you start with. And so then, as we just saw on the previous slide, with further increase of sodium hydroxide, we approach the equivalence point, which is right here, and the pH at that point is about 8.7, as we saw before. And with further increase in sodium hydroxide addition, the pH goes up further and eventually winds up at 12 point something. So this is the case for this red line is for acetic acid, which has a Ka of about 1.8 times 10 to the minus 5. How would it look for different weak acids that have different Kas? Well, they're summarized on this next figure right here. The curve for the strong acid that we just saw is this bottom red line right here, where it started out at a pH of 1 and wound up at a pH of 7 at the equivalence point, which is right here. Okay. And so the remaining red lines on here are the titration curves for weak acids with different Kas, ranging from 10 to the minus 2, this one, all the way up to 10 to the minus 10, which is this one. So it covers 8 orders of magnitude. Our acetic acid, which is around 10 to the minus 5, is right in between the 10 to the minus 4 and 10 to the minus 6 curves. So it would be a curve right about in between these two, like this. Okay, and so as we approach the equivalence point, we know that the pH is around 8.8, close to 9, and that was this point right here. The half equivalence point was down here, right about here, and so this whole region is called the buffering region again. But now, what about for acids that are stronger and weaker than acetic acid? Well, as we might expect, for a Ka of 10 to the minus 2, which is about 3 orders of magnitude stronger than acetic acid, the curve is actually more closely resembles that of a strong acid. It's only slightly higher than the strong acid curve is, and the equivalence point winds up being not a whole lot different than 7. In fact, it turns out to be just a little above 7. You can't see it on here because of the way these lines merge, but the pH is just around 7.2 or 7.3 or something like that, rather than 7. But here's 10 to the minus 4. Now the increase is noticeably more gradual than it was for 10 to the minus 2. It winds up, the equivalence point now is up in here somewhere. I can't tell exactly where on these curves. Here's 10 to the minus 6. Now it goes up, the starting pH is even higher, and it winds up being a sharper shoulder here, winds up with an equivalence point up here somewhere. Here's 10 to the minus 8, and finally 10 to the minus 10. For a weak acid with a Ka of 10 to the minus 10, you can see that even the starting pH is about 6.5 for these concentrations. And so it's a very weak acid indeed. But notice what is more significant. As the sodium hydroxide is added, the pH does increase, as you expect. It winds up coming very, very gradually. In fact, the equivalence point virtually cannot be discerned when the Ka is that low. Even for 10 to the minus 8, the equivalence point is right around here somewhere. But for 10 to the minus 10, it's virtually impossible to detect because it doesn't have any curvature at all at what we know is the equivalence point, which should be 50 milliliters. And so you can see that the shape of the curve for very small KAs can make it very difficult to actually determine the true equivalence point. And there are other ways of doing this, instrumental ways, but certainly by simply observing the pH, it's not at all obvious where the equivalence point would be. In this case, we know where it should be because we know what the starting concentration was and what the concentration of the sodium hydroxide is. So we know the equivalence point for all of these has to be in this blue band here. But if you try to discern it just visually, you can see that it's virtually impossible to detect. So what about for a weak base with a strong acid? Well, the shape of the curve is very similar. It's like a mirror image of the one for the weak acid strong base titration. In this case, we're titrating a weak base with a strong acid, hydrochloric acid. The weak base in this case is ammonia. It's just NH3 dissolved in water, and we're titrating it with hydrochloric acid, which of course is a strong acid. So now in this case, the pH with no added HCl starts out high. It's 11, which turns out to be the pH of a 0.1 molar solution of ammonia in water. With added hydrochloric acid, the pH starts to go down, just as we saw for the weak acid, it starts to go up. And we reach the half equivalence point again at 12.5 milliliters right here. And so at that point, again, we have a buffer. And if we start with ammonia as the actual weak base we're titrating, we have at this point a solution that is half ammonia and half ammonium ions. And so the pH at that point will be the pKa of the ammonium ion, not ammonia, the base. With further increase in added HCl, the pH continues to gradually go down until we get closer to the equivalence point, in which case it starts to decrease more sharply. The equivalence point we know has to be at 25 milliliters because that's the volume of ammonia solution we started with. But now at the equivalence point, what do we have? We have a solution, essentially all of the ammonia has been neutralized by the hydrochloric acid. So we have at the equivalence point only ammonium ions in solution. We essentially have a solution of ammonium chloride. And ammonium chloride will give a weakly acidic solution because ammonium ion is the conjugate acid of ammonia. And so the pH turns out to be about 5.27, which is just a mirror image of what we saw for the acetic acid, which was at about 8 point something. So the differences again here between the strong acid, strong base titration and the weak acid and weak base titrations are that the equivalence point consists of the conjugate acid, in this case of ammonia, or the conjugate base, acetate, of acetic acid, at the equivalence point. And so the pHs for that reason are either lower than 7, in this case, or higher than 7 in the case of titrating a weak acid. So again, with further increases of HCl, the pH continues to go down. And so at this point, any point beyond about here, the pH is determined almost entirely by the hydrochloric acid that we've added. The ammonium ion isn't contributing to this lower pH at all. So those are the situation for a strong acid, strong base titration, which we talked about first, and then the strong acid, weak base titration, or the weak acid, strong base titration, which wind up with pHs either less than 7 for titrating with a strong acid, or greater than 7 for titrating with a strong base at the equivalence point. What about for a weak acid, weak base titration? Well, the situation now is again different. It doesn't resemble either of the ones we've just talked about. And so if you think about it, if we start with a weak acid, let's say acetic acid, and we titrate it with a weak base, ammonia, here's the starting point again, as we saw before. If we have a 0.1 molar solution of acetic acid, which is indicated here, we remember that the pH was around 2.8 or 2.9, something like that. And as we add ammonia now, ammonia is the base that's titrating the acetic acid, but it's a weak base, not a strong base. So what happens is the pH will start to gradually go up. We reach the half equivalence point, which has no particular significance in this case, other than the fact that we've neutralized half of the acetic acid and we've used up half of the weak base ammonia that we've added. And so eventually when we get to the equivalence point, we've added exactly the amount of ammonia needed to titrate or chemically balance the amount of acetic acid we had. So what we have at the equivalence point for the weak acid, weak base titration is itself a buffer. We have a solution of ammonium acetate. Okay, we started with acetic acid, we titrated with ammonia. The ammonia, as it reacts with the acetic acid, is being converted to its conjugate acid, which is the ammonium ion, and the acetic acid is being converted to its conjugate base, which is the acetate ion. So what we have is a solution only of ammonium acetate and no other ions. Now, why do I call this a buffer? Because the buffers we talked about previously consisted of a weak acid with its conjugate base, or a weak base with its conjugate acid, where in fact the two conjugates are chemically related to each other, but they don't have to be. In this case, we have a weak acid, ammonium, which can act as an acid and donate a proton, and a weak base, acetate, which can accept a proton. And so indeed, this is a solution of a buffer. And that's the difference between titrating a weak acid with a strong base or a weak base with a strong acid, in which case at the equivalence point, you simply have a solution of a salt. At the equivalence point for the weak acid, weak base titration, we have a buffer itself. And the equivalence point corresponds to this ratio of 1-to-1 of ammonium ions and acetate ions, which means we've exactly neutralized the acetic acid with an equal number of moles of ammonium. So here's the situation. And we're not going to go into all the individual calculations, but what's going on here, for the titration of a weak acid with a strong base, or a weak base with a strong acid, as we just looked at in the two preceding cases, the solution at the equivalence point consists of a salt of the conjugate base of the weak acid, in other words, sodium acetate for acetic acid titration, or for which the pH is greater than 7, or the salt of the conjugate acid of the weak base, for example, ammonium chloride, when we titrated ammonia, for which the pH is less than 7. And prior to reaching the equivalence point, in both cases, the solution consists of a buffer. For example, acetic acid plus acetate ions, or for titrating ammonia, a solution of ammonia and ammonium, which is also a buffer. However, in the titration of a weak acid with a weak base, for example, acetic acid with ammonia, as we just looked at above here, the solution at the equivalence point consists of a buffer, the ammonium acetate. And the pH is determined by the Ka and the Kb of the weak acid and the weak base, respectively. Turns out it's related like this, and I'm not going to go through the derivation to show where this comes from. It's simple enough, and if you look at the expressions for weak acids and weak bases and the Kw, you'll see how this comes about. But the pH, of course, is minus the log of the hydronium ion concentration, which is minus the log of this square root expression, where Kw, of course, is 10 to the minus 14. It's the Kw of water. And the ratio of the Ka for the weak acid component, in this case, it would be the ammonium ion, and the weak base component, which is the acetate ion. Well, because the Ka for the weak acid is related to the Kb of its conjugate base through Kw, I know this is a lot of wording and you can convince yourself of this later, and the Kb of the weak base is related to the Ka of its conjugate acid, also through Kw. That's where this expression in the square root sign comes from. So now, if we have a case which happens to be true for ammonium acetate, coincidentally, that's all it is, it's just a coincidence. It just so happens that the Ka of acetic acid is equal numerically to the Kb of ammonia. They're both 1.8 times 10 to the minus 5. In that particular case, for ammonium acetate, this ratio is 1. So all that you have then is the square root of Kw, which is 7, and minus the log of that is a pH of 7. And so that's why for our particular case of ammonium acetate, the equivalence point is at a pH of 7. But that's purely coincidental. It's based on the fact that the Ka and the Kb of acetic acid and ammonia numerically are equal to each other. for the vast majority of cases, that won't be true, of course. All right. So now, what we've talked about, we go back to our summary of points here. What we've talked about so far have been different kinds of acid-base titrations in which the pH was measured in some quantitative way by a pH meter, for example, so that for all of those titrations, we knew exactly what the pH was numerically. What about for a case where we don't have a pH meter, or where we're going to rely on the chemistry of the titration itself to reveal where the equivalence point is? In this case, we can use what are called acid-base indicators. You've all heard of these, phenolphthalein being probably the most common one. Methyl red is another very common one. You've probably heard about these in your high school course. And so now we're going to talk about the use of acid-base indicators, which are basically color changes that correspond to pH changes. They're not as numerically accurate, of course, as a pH meter, but they give an indication of when something has changed from one state to another. Acid-base indicators are basically weak acids themselves that have one color in their acidic form and a different color in their basic form. That's the only difference. And so when the pH changes by a sufficient amount, that amount depends on what the indicator is. When the pH changes by a sufficient amount, the color of the indicator will change. And we can use this as an indicator that something has occurred to cause that pH change. Well, the reason that this can work for different kinds of indicators is because this is just a small collection of them, but it includes the most common ones. Here's phenolphthalein down here. Methyl red is not on here, but methyl orange is, and there are several others. They all have the characteristic that they have one color in a certain pH range and a different color when the pH changes by a certain amount. And the pKa's of all of these things are shown here. So you can see that thymol blue is the most acidic of them, and so its color change will occur at the lowest pHs. In fact, thymol blue changes from, they call it thymol blue even though it doesn't involve blue color. Thymol blue changes from a red color in its acidic form to a yellowish color in its basic form. And it does that in a pH range that's fairly low, between 1.2 and 2.8, right? And as you look at these various other indicators, their pKa, this is the pKa of the acidic form. The pKa is shown here with increasing numbers so that they correspond to higher pH ranges where they change colors. Litmus, one of our friends that we've used a lot. Litmus is most often used by impregnating paper with it. So you can use litmus paper to determine a pH change for an acid and a base. It turns out that the pKa for litmus is about 6.5, okay? And as a result, the range of its color change is close to 7. It's between 5 and 8. And that's the reason why we commonly use litmus paper to tell when something is an acidic solution, meaning pH less than 7, or a basic solution, pH higher than 7. Well, the actual range is about 5 to 8. But as we saw when we looked back at these, go back up to this one here. As we saw when we looked at the quantitative values of the pH changes, yes, it's true that the equivalence point is only at one particular point here at a certain pH. But because the change in pH for very, very small added amounts of added base is very, very small for, you can see in going from 24.9 up to 25, the pH changes by 1.5 units. So the pH change is very large for very small additions of the added base. That's the reason why we can use indicators like this that have a range of their color change, because in fact, the amount of added solution during the titration is very, very small over this range. And that's why they're useful. Here's phenolphthalein. Phenolphthalein has a pKa of 9.4. And so it actually changes its pH in beginning in a basic region. The pH has to be about 8 before the color change will occur from colorless to that pink color we're familiar with. Nevertheless, this is still useful for simple acid-base titrations, especially for strong acids and strong bases together, because the amount of added base in titrating a strong acid is so tiny at near the equivalence point that having the pH start changing at 8 instead of 7 is just as useful as if it changed at exactly 7. So this is just a small range of these things that have different kinds of colors here. They're shown here, not very accurately because this is just a graphic color here. A real solution doesn't look that blue or that red or whatever, but that's what they're for. Here's another set of values for these things for other indicators, and you can see it shows the color change range, the color change in pH ranges that are. Here's our phenolphthalein case again, where it starts changing at about 8 to 10 range, something like that. Here's phenolphthalein, the one that we're all familiar with or have used. Phenolphthalein molecule looks like this. Okay, this is its acid form when the pH is sufficiently low. It turns out that just because of its nature, this carboxylic acid group here does not gain or lose a proton when phenolphthalein changes color. The protons that matter are these two right here, this one and that one. Those are the ones that will get lost when the pH gets high enough. In other words, when it starts changing to its basic form. The basic form looks like this. Okay, the bottom part is still the same. These two protons are lost when the pH gets high enough, and so the molecule winds up looking like this now. One of the oxygens actually changes to a double bonded oxygen to this. It's not even a benzene ring anymore, and the other one has simply lost a proton to form the O- ion here. So the difference in color is that this stuff in aqueous solution is colorless, and this stuff is a light to a dark pink, depending on how strong the base concentration is. So this is a simple example, and some of these you can't see as well, I admit, but this one is a very interesting little set of vials that they have here. That's why I included it in the lecture notes. These are or several different indicators, lettered from A to H: thymol blue, thymolphthalein, Congo red, and so on. Phenolphthalein is F, for example. And those correspond to these letters A, B, C, up to H on the letters up for these numbers, these rows here of the different indicators. Across the top, which is even more difficult to see, are the pHs for each of these. It starts at 1 in this first column of vials, all the way up to 12 in this last column of vials over here. And so it gives you a more realistic look at what these color changes are like, rather than the simple color changes shown on the previous bar graphs up there. For example, phenolphthalein is letter F, which is this row right here. Okay, and as you can see, when the pH is anywhere up to a pH of 7, the solution is colorless. Virtually, it looks like water, as we already know. At a pH of 8, it already has a pink color, and at still higher pHs, it gets a little bit darker pink, but it's still this change between 7 and 8. So it shows why phenolphthalein is such a useful indicator for determining when the pH is close to 7. It actually changes a little bit higher than 7, but you can see what these colors look like. This last one down here, row H, is a universal indicator. You've already used this in lab a little bit. And they actually these universal indicators consist of a mixture of several different indicators, including some of the ones already up here. But they're useful because they show not just a pH change from acidic to basic or basic to acidic, but a lot of pHs in between at the extremes. And so, as you can see, at a pH of 1, this universal indicator has this reddish color. As the pH gets higher, 2, 3, 4, it starts to turn a little orangish red. At a pH of 5, it's already a yellowish orangish color right here. At a pH of 6, it's kind of a light green. At a pH of 7, it's a darker green. At a pH of 8, it becomes a kind of bluish green color. and so on. So at a sufficiently high pH, it's kind of blue. So as a result, you can use this universal indicator, as it's called, and there are several versions of this or different combinations. You can use the universal indicator not just to tell when the solution has gone from acidic to basic, but an actual approximation of the actual pH. You can tell the difference between a pH, for example, here of 5 and a pH of 7. Instead of it'll change from a yellowish orange to a green, which is easy to detect. Most of these universal indicators are used on papers. They're soaked in paper, just like litmus is. So I show this because it's an interesting little photograph that shows the actual colors of these indicators at different pHs. Now, we talked about the titration of weak acids with strong bases or weak bases with strong acids and of strong bases with strong acids. But all of the examples that we looked at were what are called monoprotic acids and monoprotic bases. Acetic acid is a monoprotic acid. Ammonia is a monoprotic base because in both cases they either gain or lose one proton. But we've already started talking in the previous lecture a little bit about dicarboxylic acid or diprotic acids as they're called, because they all have 2 protons to donate or 2 protons to accept, and it's a base. The dicarboxylic acids are much more common than diprotic bases. Here's the simple dicarboxylic acid that we talked about last time. And here I've underlined the first letters again. So here's our little friend, oh my, such good apple pie, sweet as sugar. Remember that? And the structures of them are what we looked at before. Blow this up a bit, you see these numbers a little bit better. The difference between all of these what I call simple dicarboxylic acids is that they essentially consist of 2 carboxylic acid groups, the COOH group, separated by from 0 up to 8 CH2 groups. In other words, the 2 carboxylic acid groups get farther and farther apart the longer the molecule gets. We saw this, some of the results of this in our last lecture. Oxalic acid is the smallest possible one. It happens to have the largest K1. As you can see, all of these K1s are expressed in terms of 10 to the minus 5 with some different prefix, so you can see the difference in the sizes of the values. The K1 for oxalic acid is 3,500 times 10 to the minus 5. Malonic acid is 25 times smaller than that, 140. And then starting at succinic acid, they're on the order of units times 10 to the minus 5. The K2s are about the same way. The K2 of oxalic acid is 4 times 10 to the minus 5, which is almost 1,000 times lower than K1 is. And then starting at malonic acid and so on, they're almost the same. They don't vary too much. They're all on tenths of units times 10 to the minus 5. In any case, you can see what these K values are for various carboxylic acids. A little sidebar about these things, which really is not related to the acid-base properties, but I think it's interesting anyway. If you look at the first 5 or 6 of these dicarboxylic acids here, notice what happens to the melting point. All of these are solids. Even the lowest molecular weight one is a solid. They look white. They all look like white crystals or white powders. Melting point of oxalic acid is 189 degrees C. The melting point of malonic acid, which has a higher molecular weight, has a much lower melting point. It's 50 degrees lower. Then succinic acid is higher again. It's almost the same as oxalic acid. Then glutaric acid is lower again. Then adipic acid is higher again. Notice as you go down these melting points that the melting point is higher, lower, higher, lower, higher, lower, and so on. And they correspond to an even or odd number of carbon atoms in the oxalic acid. The odd numbered ones, the even numbered ones, like oxalic acid, succinic acid, adipic acid, and so on, have higher melting points. You see that? And the ones with an odd number of carbon atoms, malonic acid has 3 carbons, the 2 carboxylic acid carbons and the CH2 group in the middle here. It has 3, so it's an odd number of carbon atoms. Its melting point is lower. An even number is higher, odd number is lower. Well, the same pattern is shown in the solubilities. All of these are either fairly soluble or slightly soluble in water. But notice that the solubilities have the same even-odd pattern, but in opposite that of the melting point. The ones with the higher melting points have lower solubilities. The ones with the lower melting points, higher solubilities. Lower, higher, lower, higher, lower, higher, lower, and so on. Now, this comes about, as it turns out, because of the structure of the solids. The ones with an even number of carbon atoms have molecules that pack together more efficiently in the solid than the ones with odd numbers. And the reason is because with an odd number of carbons, either 1 in the middle, 3 in the middle, 5 in the middle, and so on, because of the tetrahedral shape around the CH2 group in the middle, compared to the trigonal planar structure of the carbons that are the carboxylic acid carbons, each one of these that has an odd number of carbons in it has a twist that makes the molecules pack together not as closely, which means they're easier to melt and they have a higher solubility. It's just an interesting little side effect. That it's called the even-odd effect in dicarboxylic acid. Okay, having said that, what do the titrations of these things look like? All right, let's look down here at the case for oxalic acid, the simplest one. All right, oxalic acid titration looks like this. Now, just as we would expect for a monoprotic acid to have one equivalence point, a dicarboxylic acid we would predict should have 2 equivalence points, and it does. Right? Here's in this case, it doesn't give actual volumes of added base. It's just called the progress of the titration. And this over here shows the pH at various points. So the initial solution, and I don't know what the concentration is, it doesn't say it on here, but the initial solution is pure oxalic acid. It has a pH of around 1, so it must be a fairly high concentration. As the titration proceeds, which means we must be adding more base of some concentration to it. What happens as the base is added, of course, is that the pH increases somewhat until we get to this point right here, which is the first equivalence point. At that point, we have made an equivalent of oxalic acid. Here's what oxalic acid looks like. Here are those 2 carbons that are both carboxylic acid carbons. That's the carbon oxygen double bond, and here's the OH group. Same thing on the other carbon right here. And so as the titration proceeds, and remember that these protons, this one and this one, are lost successively, not both at the same time. When a proton is lost, it forms a hydrogen oxalate ion, which is H1 C2O4 minus 1. It's this species right here. Right? It shows you the structure right here. It's lost the one of the protons from one end of the molecule, and so this end has lost one of its only proton, and so now it's a CO2 minus group. The other end is still not, because the protons are lost in succession. So what we have at this first equivalence point is a solution of the remaining oxalic acid, the half that has not been made an equivalent yet, H2C2O4, same as the original one, and the same amount of HC2O4 minus. So what we have at the equivalence point, of course, the first equivalence point, is a buffer. We have a buffer of oxalic acid and hydrogen oxalate. Okay, and it turns out that for oxalic acid, that occurs at a pH right around 3, right here. Okay, so as we continue to add more base, whatever the base is, let's say sodium hydroxide, the pH continues to go up. At the half equivalence point, now we've produced some oxalate ion. All right, this half neutralized species has lost its other proton. Part of it has. The other half is still there with its proton. And so what we have at this point is a solution that consists of equal amounts of hydrogen oxalate and oxalate. Finally, when we get to the second equivalence point right here, at pH around 8.5 or thereabouts, All right, what we have is a solution of oxalate ions. And depending on what we titrated it with, let's say sodium hydroxide, this would be a solution of sodium oxalate. Now, because oxalate is the conjugate base of an oxalic acid, actually it's the conjugate base of hydrogen oxalate, right? But because it is a weak base, the pH at that point is higher than 7, just as it was for acetic acid, where the pH was also higher than 7, because at the equivalence point, we had a solution of sodium acetate. And so dicarboxylic acids will look like this, depending on what their Kas are. Now, because the Kas for the different oxalic acids start changing by a lot, as you go from oxalic to malonic to succinic, the Kas are changing by 3 orders of magnitude. What happens to the titration curve is that the equivalence point the equivalence points become less and less distinct. And so at very low Kas, even this second one is much more gradual. It kind of resembled that 10 to the minus 10th Ka we looked at for comparing Kas before. But anyway, all the dicarboxylic acids will behave in this same basic way. Here's in a situation for phosphoric acid. Now, for phosphoric acid, I'm going to show you 2 different figures to emphasize what's going on here. Phosphoric acid, of course, has 3 protons to lose, so it should have 3 equivalence points. What you can see here, this looks like those alpha curves we looked at in the last lecture, where we're looking at the concentrations, the relative fraction. We're looking at the concentrations of the various species as the pH changes. At very low pH, phosphoric acid has only 1 species present, H3PO4. Now, this very low pH, in case you're thinking about it, of a pH of 0, you can't get a pH of 0 with a 1 molar solution of phosphoric acid, because it is still a weak acid. And so the pH comes about because it contains a lot of hydrochloric acid, let's say. Something was added to make the pH be 0. Well, when the pH is that low, all of the phosphorus-containing species are H3PO4. So that's why the fraction is 1 up here. So as the pH increases, which it will do if we start adding a base like sodium hydroxide, which is what we would do if we're titrating it. All right, as we start adding increasing the pH by adding a base, the concentration of phosphoric acid decreases, the concentration of its conjugate acid, dihydrogen phosphate, the minus sign is not shown here, but this is H2PO4 minus 1. The concentration of its conjugate base increases, and so at some point right here, when we have an equal amount of both of them, the pH of about 2, right here, there's an equal concentration of both this and this, so the pH, as we've seen before at that point, is the same as the pKa1 phosphoric acid. Now, with further addition of a base to make the pH go higher and higher, we're not showing the actual titration curve at this point, just these alpha curves, but you can see what's happening. The H3PO4 is gradually going down, eventually reaches 0, and the H2PO4 reaches 1. So at this pH right here, which is around 5-ish, right? All of the phosphorus-containing species are the dihydrogen phosphate ion. And as we saw in the last lecture, the pH at that point is the average of the 2 pKa's of phosphoric acid, the average of pKa1 and pKa2. Now, with further increase of pH by some base being added, the concentration of the dihydrogen phosphate now starts decreasing. The concentration of its conjugate base, hydrogen phosphate minus 2, again not shown here, increases until at a pH of about 7, concentrations are the same. By definition, at that point, the pH is the same as the pKa2 of phosphoric acid, which turns out to be right around 7. With further increase in pH by adding more base, concentration of the dihydrogen phosphate decreases, concentration of its conjugate base, hydrogen phosphate, increases until at a pH of just below 10, all of the phosphorus-containing species are the hydrogen phosphate minus 2 ion, which has a fraction of 1, and everything else, the other possible species, are not present at this pH. Again, the pH at that point, as we saw the last time, is the average of the 2 pKa's, pKa2 and pKa3, phosphoric acid. So now, with still further increase in pH by added hydroxide, the concentration of the hydrogen phosphate decreases now. The concentration of its conjugate base, which is phosphate -3, none of these are showing the charges as they should. But this is PO4 -3 here. The concentration of phosphates increases, concentration of hydrogen phosphate decreases until at a pH of about 12, their concentrations are equal, and so that is the pKa3 of phosphoric acid. With further increase in pH coming about by adding hydroxide, the concentration of hydrogen phosphate continues to decrease, concentration of phosphate increases until at a pH of 14, it's the only phosphorus-containing species present. Now again, as I said, for the pure H3PO4, you cannot get a solution with a pH of 14 just from phosphate ions. In order to get the pH that high, this must have a lot of sodium hydroxide or some other strong base in there. Nevertheless, phosphate is a strong base. A solution of sodium phosphate will give a pH of something like 12, as a matter of fact. So phosphate is a fairly strong base. Now, what does the titration curve look like? Well, here, and I'm sorry, this is cut off at the bottom. This is the titrant volume added. And I don't know what the units are because they're cut off. We can call them milliliters if we like, or something else. But this is the volume of added base, say sodium hydroxide. So as we saw in the preceding figure for phosphoric acid, the initial pH now, which is not the case here because we're not starting at a pH of 0, the initial pH is whatever it would be for phosphoric acid. In fact, it's a little below 2. That's the pH of let's say, a 0.1 molar solution of phosphoric acid. As the volume of titrant is increased, as we add sodium hydroxide, we get to the point where we've had 1/2 of an equivalent. That's what this missing unit is here. You can't see. It's called equivalence. We've added 1/2 of the amount of hydroxide needed to completely reach the first equivalence point. And so at that point, the pH is the pKa1. We're at this point right here, okay, where the pH is 2. You can see that's where we're at, pH of 2, right? And so with further increase of hydroxide, until we get to the one full equivalent, that's what this is right here, one equivalent of hydroxide added, we've now reached the first equivalence point. This is the point at which the pH is equal to the average of the pKa1 and the pKa2, right? And so we've reached this point right here. So as we continue to add more hydroxide until we get to 1.5 equivalents, now we're at a pH of just a little, right around 7 or a little slightly higher. So we're at this point right here, right around 7, okay? And at that point, the pH is the pKa2 of phosphoric acid, right? With more addition of base hydroxide until we get to 2 equivalents. Now we've added 2 moles of hydroxide for every starting mole of phosphoric acid. We get to the second equivalence point, which occurs right here, right? And at that point, we're at a pH of just under 10, which means we're right about here, saw in the preceding figure, right? And the pH at that point is the average of pKa2 and pKa3. Finally, when we reach 2.5 equivalents, we're at a pH of about 12, which is right here, okay? pH is slightly right around 12, okay? And then with further increase of added hydroxide until we get to a full 3 equivalents, we've now added exactly the number of hydroxide ions as we had moles of phosphoric acid to begin with. In other words, we've added the same number of hydroxide ions as hydronium ions that were possible at the beginning. And so the pH, you notice, hasn't changed very much in this figure. It's still virtually 12. You'd say, well, here, dihydrogen phosphate went down to 0 and the phosphate went all the way up to 1. Well, you can't actually have that if all you have is a solution of phosphoric acid that's been neutralized. The reason that the pH hardly changes is because at this point, what we have is a solution of trisodium phosphate. And the pH of that solution happens to be right around 12. It's hardly any different than the pH was at this point right here, where we had equal amounts of the two. In fact, The point being, you can't get much higher than equal amounts of the two. You can only get to around right about up here somewhere, okay, for a pure, like when you reach exactly 3 equivalents. Now, if you continue to go beyond that and add more excess sodium hydroxide, now the pH can get higher, but not by much because you're already at 12. And so adding more hydroxide doesn't increase the pH very much more. So that's what a triprotic acid titration looks like. Now we're going to end with just one final example of something that is, I'll change this to 90% here, I think works well. Yeah. Is an example of an interesting kind of multiprotic compound, and that's an amino acid. We're going to look at just one of them, a very simple one, alanine. Alanine is one of the what are called essential amino acids for mammalian life. Alanine looks like this. It's called an amino acid because it has the carboxylic acid group here with its donatable proton, the blue one here. But it also has an amine group on it as part of the molecule. It's on another carbon atom, but it's an NH2 group. Because an NH2 group is like ammonia. If all the rest of this whole molecule were just another hydrogen, you'd have ammonia. But in this case, the amino group acts like a base. It can accept a proton, which is exactly what it does if the pH is low enough. If the pH is sufficiently acidic, the amine group will accept the proton to form an NH3 plus group on the molecule. And that's what we're going to look at now as we look at the titration of an amino acid. This amino acid has one carboxylic acid hydrogen, but it also has an amine group. And for that reason, it behaves as if it were a diprotic acid. It's not a dicarboxylic acid, but it acts as if it has two hydrogens to donate, depending on the pH. So here, let's look at what happens if we titrate this alanine with hydroxide. Here they show it as HO minus, but these are the equivalents of HO minus. So an equivalent means enough to neutralize half of these things, one of them, 1.5 of them, or both of them. So that's what the equivalents of 0.5, 1, 1.5, and 2 represent. So here, again, if we start at a pH of 0, and we can only start at that low a pH if some strong acid was added to the solution. The pH of just alanine in solution by itself will not give a pH as low as 0. So we must be starting with a solution that's been acidified sufficiently to cause the pH to be 0. Well, at that pH, this is the only species that's present. The carboxylic acid hydrogen is still there, of course. The pH is so low, it hasn't donated anything. But the amino acid, the amino group, is now an NH3 plus group. Because the pH is low enough, it has become protonated as NH3 plus. Okay? So now, what happens as we start to add hydroxide? When we get to half an equivalent, that means we've added enough hydroxide to neutralize half of these protons that are here. The one that gets neutralized, and what we wind up with is a mixture of two species. We have the initial species that was present at a pH of 0, this one, okay? And we have half of the carboxylic acid hydrogen being donated, okay? So at that point, we have what is the pKa1 of alanine. Now, this is not a buffer, though. You can't view it as a buffer because these two are not related in that sense, although they could react with either acids or bases, but it's not conventional to call this a buffer solution. Now, when we add enough more hydroxide to get to an equivalent of 1 equivalent, what we have is all of this stuff. In other words, with 1 equivalent of hydroxide added, we've essentially neutralized all of the carboxylic acid protons, but we haven't removed any of these NH3 protons, which are donatable. It takes a lower pH, a higher pH for that to happen. And so that's what happens as we add more hydroxide. At this point, if this were a simple weak acid, we would have had there wouldn't be this amino group here. We would have completely neutralized the acid, and we would wind up with this salt of its conjugate base. But because this is an amino acid, if we add another half equivalent to get us up to 1.5, now we still have half of this stuff left, but now we've neutralized the other half. So now we have an NH2 group here. We have a mixture of these two species at this point. And so at that point, pKa2 is 9.7. It's the average of the pH. That pKa2 is the pH at that point, which is just under 10, as you can see here. Again, this is not referred to as a buffer, even though you could say, well, this could accept a proton and this could donate one, but that's true, but this is not referred to in terminology as a buffer. Finally, when we've added a full 2 equivalents, now we have neutralized both protons, the one that used to be here and the one that started out as an NH3 group at the other end of the molecule here. And so all that's left now is a deprotonated alanine, a deprotonated amino acid, that's referred to as an alanate ion because of that complete neutralization. So we've now covered a variety of these acid-base titrations, ranging from strong acid, strong base to strong acid, strong base type titration, strong acid, weak base, weak acid, strong base. We've talked about indicators. We've talked about polyprotic acid titrations, where there are multiple equivalence point and buffer regions that correspond to the number of acidic protons. And so we also noticed in the case of a triprotic acid like phosphoric acid that the successive equivalence point become increasingly indistinct as the Ka approaches Kw. That's the reason why we saw the thing become increasingly indistinct here. Okay, where we said at Ka of 10 to the minus 10, we could increasingly see or be unable to see where the equivalence point is. And the reason for that, essentially, is because we are, reduce this a bit, and the reason for that is because we're getting closer and closer to the Ka being equal to Kw, at which point it behaves the same as pure water. And that's the reason why the equivalence point becomes increasingly indistinct. It's because the Ka is approaching the Kw for water. And that's the reason for that behavior. So next time we'll talk about something other than weak acids and weak bases. And you'll see how some of the stuff is all related to that as well.